The graph of log base a of x, where the base a is some number bigger than 1, looks something like this. And when the base a is between 0 and 1, we end up with a graph that looks something like this. And based on those graphs, we can talk about the properties of log functions. And you'll see some connections between these and the properties that we talked about for exponential functions because of their relationship as inverse functions. So first of all, both of these graphs stay to the right of the y-axis, which means the domain is only positive numbers, 0 to infinity. And keep that fact in the back of your mind because it's going to show up with something that we're doing in a later section. The range, however, is all real numbers because we have all of our negative y values covered this way and all of our positive y values covered this way. Just as the x-axis was a horizontal asymptote for our exponential functions, the y-axis is a vertical asymptote for the log functions, because as we're going down, we're getting closer and closer to that y-axis, but we never actually touch it or cross it. And the same way with this other graph over here, as we go up, we're getting closer and closer to the y-axis, but we never touch it or cross it. And because we never touch or cross the y-axis, these functions have no y-intercepts, but they both do have an x-intercept of 1, 0. So this point is at 1, 0, and this point is at 1, 0. And both of these graphs pass the horizontal line test, which means our log functions are one-to-one functions, and we know they have an inverse, which is the exponential functions, because that's where these come from. Now, if we want to talk a little bit more specifically what the graph of a log function looks like for a specific base, we can just plug in numbers. So if we want to graph the log base 2 of x, I'm going to plug these different values in, and notice that I have them in the f of x or the y column. So I'm going to be plugging these numbers in for y and figuring out the x value that corresponds with them. And that's because if I want to use the -1, so I want to find the log base 2 of x is equal to -1, and I want to find the x value that makes that true, I can think of this as an exponential equation. This is the same as 2 to the -1 is equal to x. And then 2 to the -1 is the same as 1 over 2, or 1/2. So that tells me that when x is 1/2, the value of this function, or the y value, is -1. So then to find the x value that corresponds to 0, log base 2 of x equals 0, as an exponential equation, this is the same as 2 to the 0 is equal to x, and 2 to the 0 is just 1. So when x is 1, f of x is 0. And when I stick a 1 in place of the f of x, I'm looking at the log base 2 of x is equal to 1, which is an exponential equation, is 2 to the first equals x. And 2 to the first is equal to 2. So when x is 2, the log base 2 of 2 is 1. And now I have this set of ordered pairs that I can graph to figure out what the graph of log base 2 of x looks like. So we've got 1/2, -1, which would be located here, 1, 0, which is here, and 2, 1, which is here. And then I'm just going to connect those points with a curve that looks similar to this one. So we end up with something like that for the graph of log base 2 of x. So for log base 1/3 of x, I'm going to do something similar. I'm plugging in the same values in place of the y. So to figure out the x value that goes with a y value of -1, I'm asking myself, 1/3 to the -1 is equal to what? Well, remember that negative exponent is going to flip this over, making it a 3. So when x is 3, g of x would be -1. So for the 0, this would be the same as 1/3 to the 0 is equal to x, which anything to the 0 is 1. And then when I have a 1 in place of the y, 1/3 to the first is equal to x, and 1/3 to the first is again just 1/3. So now I'm going to plot those points, 3, -1, 1, 0, and 1/3, 1, which we can estimate to be about there. And then I'm going to connect those points with a curve that looks like this. So we end up with something like this for the graph of the log base 1/3 of x.